Hello guys, welcome back to my channels. So today I'm going to talk about chemical bondings. So in this lectures I'm going to cover types of bondings and give some details about the backgrounds, what is importance of chemical bondings and what is factors that influencing the bonds and then I will discuss the dipole moments and ex- some examples, then MOT theories. And under this theory, I'll discuss the energy level diagrams for molecular orbitals and then bond orders and some examples in heteronuclear diatomics and homonuclear diatomics. So in this video, I will cover all these points. So let's start. So what is chemical bonding? That is the big question. Okay. So chemical bonding is something like bond formation. Okay, bond formation and bond formation due to the force. Without force, it cannot be formed the bond and bond form via uh, ionic or sharing of electrons. Okay, cation and ion are sharing one electrons that form the bonds. So this chemical bonding is force that holds atoms, ions, and molecules together to form compounds. Okay, so these chemical bonds here the atoms form these bonds to achieve more stables, lowering energy states that often by gaining or losing or sharing electrons to fulfill the octet rules. So here to obtain the stability by gaining or losing or sharing of electron of the molecules or compounds. So basically here three types of chemical bonds. One is ionic bonds. So ionic bond is the attraction between the opposite charge ion plus and minus. And covalent bond is due to the sharing of covalent bond is formed due to the sharing of electrons. And metallic bonds, the sharing of electrons that are free to move throughout the structures. Okay. So now discuss the factors that influencing the formation of ionic bonds. Okay. So first factor is ionization energy. Ionization energy, the most important factors. What is ionization energy? Actually, the ionization energy, the amount of energy that required to remove the most loosely bound electron from the isolated gaseous atom of an elements. As you can see, these examples, sodium atom in gaseous form through the ionization process. Through the ionization process, it requires some energies. Okay, 495 kilojoule mole inverse and form the ions, sodium plus ions, and lose the electrons. So this process is uh, endothermic process because here energy is required to remove electrons from the cations. Okay, So now discuss second point, electron affinity. What is electron affinity? The amount of energy released when an electron is added to isolated gaseous atoms. So here in this in this factors, electron affinity factors. So here the energy how much energy required, how much energy released when an electron is added to isolated gaseous atom. As you can see here, this is the chloride in gaseous form. When add the electrons due to the electron affinity process, it will lose some energy. Okay, so this is the exothermic process and chloride ion in gaseous state form. So last point is lattice energy. So lattice energy is the amount of energy that released when cation anions are brought from infinity to their respective equilibrium site and form 1 moles of ionic compounds. Okay, so these are the factors that influence the uh, ionic bonds. So now discuss the node points. What is node points? Uh, what is node points? So node points is here when the higher the magnitude of lattice energy, greater is the tendency of the formation of ionic bonds. And higher than lattice energy, the force of attraction between constituent ion should be high. Okay, that means the when the value of lattice energy is high, then the formation of ionic bond will be high. Okay, similarly, when the lattice energy is high, the force of attraction between constituent ions should be high. Here, the force attraction of two opposite charge is due to the Coulombic law. Okay, where F is the force and F is equal to Q1 Q2 upon R square, where Q1 Q2 are the charges and R is the distance between these two ions. Okay, so now move to the dipole moments. So what is dipole moments? Actually, here the measurements of the polarity of the molecules or any systems that representing the separation of positive and negative charge. Okay, so dipoles moments is something when a systems or molecule that represents the positive and negative charge, that shows the polarity. And this dipole moments, it's a vector quantity that show magnitudes and directions. Okay, so if the net dipole moment is zero, that means the molecules or systems is polar, otherwise non-polar. Okay, is non-polar, sorry, if the dipole moment is zero, that means the molecules will be non-polar, otherwise polars. So here is the formula to calculate the magnitudes dipole moments. So mu that symbols of dipole moments mu that represent through mu is equal to q into d, where q is the charges and d is distance between charges, and the unit of this mu, that magnitude is dBi. Okay, so here last point is the direction from less because this is the vector quantity. Okay, a vector quantity. So here show magnitude as well as direction. So here the direction from less electronegative to more electronegative atoms. Okay, so now we'll understand through some examples. Okay, So examples here, as you can see, uh, for this molecule, carbon dioxide molecules, if you see the arrow of arrow of this uh, molecules for between C and O, the direction is towards oxygen side because oxygen is more electronegative compared to carbon. Similarly, from left side, the direction is from carbon to oxygen. So here the net dipole moment is zero because both arrow is uh, 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 to opposite sides. Okay, so net dipole moment will be zero. Similarly, for this water molecules, if you draw these structures, so you will see the direction because oxygen is more electronegative compared to the hydrogen, so direction will be towards oxygen sides by both by both hydrogens. Uh, so the angle between these 104 and dipole moment towards this direction, so net dipole moment is 1.84 dBi. Okay. Similarly, third examples, trifluoroborans dipole moment is zero because the electronegativity is towards F sides. All three cases, therefore net dipole moment is zero. Similarly, other examples we can see for this zero because all are cancel out to each others. Okay, this cancel out from by this and this cancel out by this, so net dipole moment is zero. Similarly, for this is methanes cs4s, so electronegativity is towards carbon side because hydrogen is less electronegative comparison to carbons. So the electronegative arrow will be this side towards center atom side. So net dipole moment is zero. Similarly for other examples. Okay. So now discuss the MOT theories. So MOT theory is most important theory. Here we through this theory we describe the bonding by combining the atomic orbitals that form new delocalized molecular orbitals, and it is used to explain the molecular structure as well as stability and properties like paramagnetics. Okay, in this theory, electron occupy molecular orbitals with specific energy levels and filling the orbitals that determines the bond order and magnetic properties of the molecules. So here are the energy level diagrams. I will discuss in next class the energy level diagrams. So before we start, we have to know the bonding molecular orbitals and anti-bonding molecular orbitals. So these are the bonding molecular orbitals: sigma 1s, sigma 2s, sigma 2pz, pi 2px, pi 2py, and anti-bonding we denoted stars: sigma 1s, sigma star 1s, sigma star 2s, sigma star 2pz, and pi uh, star 2py, px, and pi star 2py. Okay, so now discuss the uh, energy level diagrams of MOT. Okay, so these energy level diagrams of different molecules we can draw like this. So this is 2s. 2s shows single orbitals. Okay, single orbital that represent by 2s. Actually, here we have skip this energy levels sigma 1s. Okay, so in diagram we have started from sigma 2s. So these 2s from this bonding sigma 2s and anti bonding, and 2p have 3 orbital, so these will form the recombine and form this bonding sigma 2pz and pi 2px, pi 2py. Similarly, anti-bonding form pi star. This corresponds pi star to px and pi star to py, and this sigma to pz correspond to sigma star to pz antibonding. But here we have to note down that the change in energy of MO molecular orbital is due to the mixing of molecular orbital of same symmetry. So here mixing of molecular when we mixing of in the case of mixing of molecular orbital, the energy level will be changed. So this will be higher energy than this. So this uh, will go downside and this will go upside. So as you can see, this is energy level. Sorry, y-axis shows the energy. So energy increases from down to uh, upside. Okay, so energy will high for mixing case sigma 2pz, and remaining things is same. Okay, so this is the molecular orbital diagram. So now discuss the some notes points. Okay, because every theory has some concept. Okay, so the energy levels of these molecules have been determined experimentally from spectroscopy data, and energy level generally increase as we move from left to right uh, in the following this sequence list. So sigma 1s energy is lower than the sigma star, and similarly for sigma 2s is energy higher than this sigma 1s. Similarly, this energy, that means our uh, point is energy is increases from sigma 1s to sigma star to pz set. Okay, so actually this sequence energy of this sequence is uh, for diatomic molecule atom, those atoms who shows the uh, total numbers of electron is greater than 14 or equal to greater than 14, not equal to 14. So S- so those molecules, diatomic moles whose total atomic numbers shows greater than 14, then we'll have to use this uh, sequence. Otherwise, we use the mixing of orbitals. This sequence, okay, this bottom one sequence. But here we have to know the when the diatomic molecules atomic numbers total electrons n is less than or equal to 14, like example lithium to lithium to beryllium to uh, uh, carbon to nitrogen to all these we can uh, draw the energy level by using this sequence, like mixing of orbital sequence. Here, as we remember, the this sigma 2pz or molecular orbital is higher in energy than this pi orbitals. So as you can see here, we have like here change the energy. So here, if you see, this pi comes first, then later 2pz, because here the 2pz energy is higher than the pi. Okay, earlier in diagram also we have seen. So this basically for those uh, molecules whose have total numbers of electrons 14 are less than 14, but this is those shows atomic numbers of electrons is more than 14. So for that case, use this sequence for electronic configuration purpose. Okay, so now we'll see bond order. Later we'll see the we'll take the examples of related to this energy level sequence. So now discuss the bond order. What is bond order? So bond order is something measuring the numbers of chemical bonds between the pairs of atoms. Okay, so it is calculated as a half the difference between the numbers of bondings and anti-bondings electrons. Okay, so bond order indicates that the bond strength and stability, that is higher the bond order correspond to the stronger bonds. Okay, as you can see here, represent the equations of bond order. So bond order is equal to half of the numbers of electrons in bonding molecular orbital minus numbers of electrons in anti-bonding molecular orbital. As you can see here, we have taken some examples of homonuclear diatomic molecules. So first example is hydrogen molecule, H2 molecules. So the H2 molecules have two electrons, two atoms is here. So H2, so two electron have two electrons. The configuration is electronic configuration for these hydrogen H2 molecules is sigma 1s2. So sigma 1s2 is so bond order is half of bonding electrons. So as you can see, bonding electrons is 2, anti-bonding is 0, so bond order will be 1. But hydrogen 2 plus S2 2 plus ions, it will show sigma 1 S1 because plus uh, uh, cations remove 1 electrons. So bond order will be half 1 minus 0 is equal to half. Okay. So similarly, other examples, helium 2 plus. So helium 2 plus, sorry, helium 2, it will show 4 electrons. So electronic configuration is sigma 1s2, sigma star 1s2. So bond order will be 2 is bonding and 2 is anti-bonding. So 2 minus 2 is equal to 0. So 0 bond order, this indicates that the molecule does not exist. Okay. And similarly last fourth example, nitrogen configuration is this because this total atomic numbers of electrons is 14. Okay, for this case, so 14 case we have to use the mixing molecular orbitals sequence. So here as you can see, this pi will come first and then later sigma to pz will come uh, letters. So this is the electronic configuration for the those source 14 or less than 14. Okay, so bond order will be the 10 because here you will see the bonding total bonding electron is 2, 4, 6, 8, 10. Okay, bonding electron is 10 and anti-bond means sigma star is and shows anti-bond. So anti-bonding electron is 2, 4, 4. Okay, so here is the total force anti-bonding electrons. So 10 minus 4 is equal to 6 and divided by 2 you will get 3. So so this so 3 bond order, but it will show diatomic. Okay, diamagnetics because here there is no unpaired electron is present. Similarly for uh, oxygen molecules O2, so total numbers of electron is here for 16. So you will see first electronic configuration sequence. So sigma pz will come first and later pi orbital will come. Okay, so this is the configuration. Okay, so and in last orbitals, molecular orbital, you will show one electron, single electron. So this will indicates the paramagnetic because two unpaired electron is present. And bond order you will get total bonding electron is 10 here. Anti-bonding if you calculate, you will get see that 6 anti-bonding electron. So you will get two bond orders. Similarly for neon, okay, neon 2 total numbers of electron is 20, so you will get 10 bonding and 10 anti-bonding, so you will get 0 bond order. So 0 bond order, because this anti-bonding molecule are slightly dominate over the bonding molecular orbit, that's why this neon 2 would be incapable of existence. Okay, so now we'll take the examples that belongs to the heteronuclear diatomic molecules. So these are the examples of heteronuclear diatomic molecules. So for these cases, similarly we have to calculate the bond order, as well as we'll check the uh, paramagnet, either it is paramagnet or diamagnetic. Okay, so here the total numbers of carbon 6 and oxygen is 8. So 8 plus 6, 14. 14 electron, that means we have to use mixing sequence of energy levels. So here pi will come first and later we will get sigma 2 pz. So here the total bonding is 10, non anti-bonding is 4, so we'll get 3 bond order. Okay, NO similarly for NO you will get the 2.5 bond order, and this shows paramagnetic because in last orbital you'll see the single unpaired electrons, and NO. Okay, this is same repeated example. This will show also uh, bond order uh, 2.5 means the 2.5. So bond order is 2.5, and for NO plus this will lose one electron, so bond order will be 3, and NO2 plus lose 2 electrons, so 13, bond order is so 2.5. So here is the uh, we'll see the highest bond order for NO plus case. Okay, comparison to NO minus also shows 2 bond order, so highest bond order for this case. So this is all about the chemical bonding and mm, bond orders and dipole moments. Okay, so all those things we have covered in this video. So if you found this video interesting, please do like and comments, and don't forget to subscribe my channels, and thank you for watching.